Sup physics fan, welcome to the debut episode of Physics Guy, where we'll be learning physics through exam style questions. Today we're going to be looking at the age old question of a rod moving through a uniform magnetic field at a uniform velocity. The not so good way of answering the question, and the way that will guarantee you getting full marks each and every single time. So if you're one of the students that says cos Faraday's law, cos Lenz's law, in this type of question, well then you better stick around for the next 10 minutes or so, because we're going to get you some extra marks. Now look who's stuck around. So you're one of those people that says cos Faraday, cos Lenz or whatever when it comes to explain induced EMF in a rod. Okay, so I'm going to tell you that would not fly. That would not get full marks if it was a 3-mark question or a 4-mark question. You're going to miss one of the marks. If it's just a 1-mark question, identify which side of the rod is positive or something like that, or if it's a multiple choice question, by all means. You can use the Faraday-Lenzy stuff to kind of make sense and how we will do that, right? So in this scenario, we've got the rod moving towards the right in a magnetic field going into the page. So we'll use our right-hand palm rule. Okay, so right-hand palm rule, fingers in the page. We have the rod moving towards the right, and there we say, oh, cos Lenz's law, force must oppose motion, therefore force back towards the left. And we've got our thumb pointing up the page. Okay, what's our thumb represent? Our thumb represents the flow of conventional current. Okay, so it's a flow of positive charge, which means if the positives go up the page, there must be a relative positive charge at the top and therefore a relative positive charge at the bottom. We've figured out the polarity of the rod. There's positive at the top, there's negative at the bottom. Okay, but how we figured that out was cos Lenz's law. Lenz's law must oppose motion. Now, what does Lenz's law relate to? Lenz's law relates back to direction of current. Now, in this scenario here, we just have a rod, and we assume it's like a one-dimensional rod. So the current can only flow back or forth, and that's it. It can only go one way. It can't loop around or anything like that. It's like it's the width of one electron. The electrons can only go one way. Well, the positive charges can only go one way. So there's nothing looping it back around, allowing the current to flow via an external circuit. So guess what? Current doesn't flow. So you've just based your explanation on Lenz's law. Lenz's law all to do with direction of induced current, but in this particular scenario, there is no induced current. Okay, yes, there is an induced EMF, but there is no induced current. So we need to think of a better way of explaining this scenario. So if we get the explain the induced EMF in a question, we can actually hit the 3 out of 3 or the 4 out of 4, or however many marks it's worth. Okay, it ought to be 3 or 4 marks depending on the bands that they're kind of assessing for the question. All right, so where we go with this is we actually think about, well, it's a metal rod. What is metal? Metal has 2 main parts, right? So it's got, if you've done chemistry, you've probably said this 1,000 billion times by now. So the structure of a metal, you've got the positive metallic lattice, okay, which we'll just quickly draw, a 3x3 lattice. Here is our positive metal lattice. Now, of course, all these positive ions are indeed the exact same size, and they're separated by the exact same distance, which let's say does diagram not to scale, right? Diagram not to scale. All right, and I kind of missed one down here. There we go. So there's our positive metallic lattice, okay? And it's not just protons, right? It's the entire nucleus, okay, alongside any of the inner electrons. The only things that are missing in these little positive things are the mobile valence electrons, conduction electrons, the sea of delocalized electrons. Okay, so what do those delocalized electrons do? Well, they're just heading around the lattice. They're not attached to any particular ion because, again, they are delocalized. Okay, so they're just chilling out, whatever. They're just zooming around the lattice, kind of like I do on Friday nights down the M7. Don't know why I said that. But whatever. Okay, so we've got these electrons zooming around the lattice. Electrons free to move. Positive metal ions, not so much. How do we actually figure out what's going on inside the metallic rod? Well, we say if the metallic rod is moving towards the right, then this entire lattice structure is moving towards the right. So you've got the positive metallic lattice, you've got the sea of delocalized electrons moving towards the right because the rod is moving towards the right, and that's the structure of the rod. So we would go fingers into the page, cos magnetic field into the page. These charged particles, the positive and the negative ones, they're moving towards the right in the magnetic field. So therefore our thumb points towards the right. If our thumb points towards the right, our palm points up the page, and the back of our hand, whatever that's called, the back of our hand, points down the page. All right, so That means positives experience a force up, negatives experience a force down. But keep in mind, this is the structure of the metallic lattice. The positive metal ions are actually fixed in position and they cannot move. They cannot physically displace. What can move are the electrons. Okay, so we just said the electrons experience a force down the page, okay, because they're negatively charged. The positive metal ions experience a force up the page, but again, they can't physically displace. So what happens is the electrons experience a force down the page. All of the electrons go down the page. So my question to you, if the electrons are heading towards the bottom of the rod, what is the charge on the bottom of the rod? Is it positive? Is it negative? Or is it neutral? I reckon a lot of you probably would have said that it's positive because you're used to negative things flowing towards the positive plate or positive terminal or whatever it is. Okay, this is how we differentiate between what happens in the, let's call it like the internal part of the circuit and what happens in the external part of the circuit. Okay, we'll come back to that in a few minutes. So if you said that the electrons going towards the bottom of the rod make the bottom of the rod positive, I want to explain this to you in a certain manner. And that is, before the rod moves, what's the charge on the bottom of the rod? So if the rod's just stationary in the magnetic field, what's the charge on the bottom of the rod? It starts with N. Hopefully you didn't say negative because it's neutral. Okay, there's no charge build up, or no net charge, I should say, at any point on the rod. It's nice and, let's say, it's perfectly homogeneous. Okay, so all the positive metal ions uniformly distributed. All this sea of delocalized electrons uniformly distributed. As a result, there is no net charge anywhere on the rod. Okay, so again, everywhere on the rod is entirely neutral. Then that rod moves through this external magnetic field, okay, which is directed into the page. We just said positive charges experience a force up, negative charges experience a force down. The positive charges can't move, but the negative charges can. So if the bottom of the rod before was neutral, and now the negatively charged electrons move down, well, there's more electrons there than there was before. There's more negative charge than there was before. Therefore, it becomes negatively charged. Okay, so what we'll say is it becomes negatively charged, and we'll say 3 words, and that is excess of electrons. Okay, so it's an excess of electrons, which creates this negative charge. Okay, so likewise at the top, if the bottom's negative, then the top's got to be positive. Okay, now we would not say this is due to an excess of protons or an excess of positive metal ions or something like that, because nothing's changed in terms of the positive charge. What has changed is there's some electrons which have left. Okay, they've gone. They're gone. Right, so if the negative charges flows down the rod, there's more negative charge down the bottom than there was before, therefore it becomes negatively charged. And likewise, negative charge has moved away from the top, and therefore it becomes relatively positive. We're not going to say excess of protons, we're not going to say excess of positive metal ions. Rather, we're going to say that there's missing electrons, okay, or a deficiency of electrons. So we've explained the production of an induced EMF, okay, not in terms of magical Lenz's law, even though there's no current, not in terms of a flow of conventional current, again, even if there's no current and positive charges in a metallic lattice don't move. We've explained it in terms of the charged particles in the rod moving through a magnetic field and the force on the negative charges, because they're the only things that can move. Okay, so this is something which is called motional EMF. Okay, so motional EMF is the best way of explaining production of EMF in any conductor. Okay, whether it be a rod, whether it be a two-dimensional sheet, a pendulum, all those cases where you look at eddy currents, you can explain it using motional EMF, which is like, I don't know, it's the better explanation because you can actually explain stuff. You can talk about the force on the electrons rather than just saying, I don't know, cause of Lenz's law or the conventional current flows this way. But let's address something which you're probably thinking about, and that is, you know, throughout all my time in junior school, I was always taught that the negative charges flow towards the positive and the positive charges flow towards the negative. So I'm going to draw you a little bit of a circuit. And it's just a simple circuit. Okay, and it's just, you know, a little short circuit like that. So we know from our junior schooling that the big plate is positive and the small plate is negative. And we know that the positive charge, the conventional current, flows from positive to negative. Cool, right? As we expect. But what happens when the positive charges gets here? Okay, or more correctly, electrons flow from negative to positive. What happens when the electrons get here? Do they just disappear? Like, have you ever thought about that? This is also part of the circuit. This is where the battery comes from. This is the source of the EMF. This is the energy. Now, what is this rod? This rod is the source of the EMF. So essentially what's happening is this rod is acting like the battery. It's acting like the, how do I say? It's acting like where the energy is produced for the electrons to discharge, okay, in the external circuit. Now, the only reason why electrons want to go from negative to positive is because the internal circuit has made one side positive and one side negative. Okay, so in chemistry, you do all this stuff. You do this galvanic cell stuff. I mean, what is this? What is a battery? It's a galvanic cell, okay, which forces the electrons to go one way, which means one side's going to be negative and the other side's going to be positive. So when the negative electrons flow out from negative to positive and the conventional current flows from positive to negative, that is in the external circuit because it's discharging. Okay, so it's moving along the, let's say the electric field kind of gradient. It's moving through that and it's kind of making itself go back to its lowest energy state. Okay, which is, in physics, that's where everything is happy, the lowest energy state. So what actually happens, again, in the external circuit, yes, electrons go negative to positive, but in the internal circuit, that's where energy is given to the electron to drive it across to make this side negative in the first place. What's going on here? Energy is being given to the electron to make this side negative in the first place. If I then connect an external circuit, so I connect a little loop of wire from the top of the rod to the bottom of the rod, what happens, as we would expect, the electrons come out of the negative and they flow towards the positive. Because that's the external circuit. It's the same thing as this. It's the external circuit. Okay, whereas the conventional current would flow out of the top, out of the positive, into the negative. Okay, so we've explained the production of the EMF, okay, in terms of not Lenz's law, not Faraday's law, not conventional current, but the structure of the metal. Okay, the structure of the metal and the fact that as the metal rod moves through the magnetic field, these charged particles move through the magnetic field. Both the positive and the negative charges experience a force, but the positives are fixed in the metallic lattice. Therefore, it's only the negative charges which can actually physically displace. The negative charges move to the bottom of the rod, okay, and therefore they build up there, making the bottom of the rod negative. Okay, top of the rod, deficiency of electrons, making it positive. So that's the induced EMF. That's the, let's call it the charge separation. Okay, now current will only flow if we then link the bottom of the rod or the place that's negative to the place that's positive. Okay, and what will happen is the electrons will flow out of the bottom into the top, or, in terms of conventional current, the conventional current flows out of the top into the bottom. All right, and it also says there, there is a constant net force acting to the right, which is applied to the rod. So if it's a constant net force acting towards the right, what's the rod going to do? The rod is going to accelerate. It's going to move more quickly. If it's going to move more quickly, then it's going to cut lines of flux more frequently, okay, and therefore the induced EMF is actually going to increase. Okay, so motional EMF, let's see if we can do this real quick. Motional EMF is actually given by the formula E is equal to BLV. Okay, where B is the strength of the external magnetic field, L is the length of the conductor that's in the field, and V is the speed at which the rod is actually moving. Okay, so this is really just a form of Faraday's law as we know it. Okay, EMF is, let's just say, proportional to delta phi over delta t. Okay, now how is it a form of that? So here is our rod. Okay, and there's our external magnetic field, right? Here's our external magnetic field, blah, blah, blah. And we'll call that rod of length L. Okay, so might make that rod a little bit larger. Okay, so let's get rid of this. Push, get rid of that. Make that rod a wee little bit larger. And we'll say that is a rod of length L. Okay, now keep in mind this is a solid rod. Okay, and it's also infinitesimally thin. Now, if that rod moves towards the right with a speed V, okay, now V, we know, is displacement over time or distance over time, whatever you want to call it. And let's just say it's going to be displacement over time. All right, now what is change in flux? Okay, so change in flux is going to be magnetic field times change in area over change in time. But what is the change in area? Okay, so our change in area is it's essentially the area which the one-dimensional rod has actually swept out. Okay, so let's say it goes for a certain time t, and then the rod ends up over here. Okay, ends up over here. The area that the rod has swept out is the area of where it starts compared to where it finishes, that entire area which is swept out. Okay, so what we might call this, if we just call this like the distance, okay, the distance that it has moved through, or the displacement, let's label that S actually, because I labeled it S up there. So we've got the distance of the displacement which the object has moved through. So what is the area which the object has moved through? The area which the object has moved through is just going to be SL. That's the area which the object has moved through. Okay, so A is equal to the displacement of the rod multiplied by the length of the rod. All right, so we're going to chuck that in up here, and we're going to say that change in flux is going to be B times the SL over time. If you see in there, there is displacement over time. What is displacement over time? It's velocity. Okay, so therefore we get change in flux is going to be B multiplied by our L multiplied by our V. Oh, sorry, that's change in flux over change in time, GG. Change in flux over change in time. Okay, so change in flux over change in time is therefore going to be BLV, and we know that EMF is equal to BLV. It's the same thing as EMF being equal to the rate of change of flux. Okay, it's a single one-dimensional rod, so we ignore any number of turns or anything like that. So it's just kind of nice to see that motional EMF equation actually does, tie in with Faraday's law. Okay, so hopefully that's helped us a little bit in our understanding of, why which side of the rod becomes positive, why it becomes negative. And now you can explain it in terms of forces on electrons, excess and deficiency of electrons. Remember, what excess and deficiency of electrons means is there's a charge separation. That's essentially what our EMF is. If we then connect an external circuit, then we can talk about the charges flowing through the external circuit as well, and the direction, therefore, of electron flow or conventional current. All right, so hopefully that's helped you guys. Hopefully you like and subscribe and whatever you're meant to do to YouTube channels. And we'll come out with some new content pretty regularly. But in the meantime, all the best. If you've got any comments, put them in the comment section. If you've got any questions you want me to address, put them in the comment section as well. All right, peace out, guys.